It will come in and join itself to the CH3, and Cl minus will come out. And what will you get? CH3 OH. OH will combine with the CH3 and Cl minus will come out. Suppose if you have so this is a nucleophile and Cl minus is a leaving group. This whole thing come and join itself to the carbon. Okay. So this is the reaction, but there is a mechanism also. Mechanism helps us to know how the reaction happens. Okay, whether it is a single step mechanism is actually step-by-step explanation of the reaction. So for nucleophilic substitution reaction, there are two mechanisms. One is called sn2, another is called sn1. Okay, S stands for substitution, N stands for nucleophilic, okay, and 2 stands for bimolecular, 1 stands for unimolecular. So this is actually substitution. Okay, so these are the two mechanisms, and observe what's the difference between these two, SN2 and SN1. What's the difference? How they are different from each other? So SN2 is, the name is helping us to know what is the meaning of SN2.
Yes,
SN2,
sir.
yeah, tell me.
The one is bimolecular and other one is unimolecular.
Yeah, unimolecular, exactly. Yeah, yeah. So bimolecular means what? Two molecules are involved together.
Is called bimolecular.
Yeah, it is single step. And how it happens?
Don't know, sir.
Okay, no problem. Two step or multi step. So what you can do is, suppose if you want to revise anything, let me know. Okay, we can have extra class schedule. So single step, how it happens? Suppose CH3 VR you have taken, and aqueous KOH you have taken. OH minus has more electron densities. It is minus. It will get attracted toward the carbon because it is having plus charge and Br is having minus charge. So it will come and join, and simultaneously the Br will come out. Okay, simultaneously in one step. So how many molecules are getting involved in the one step? 2 molecules, and the
Yes,
2 molecules are of, one is of one is a nucleophile, another one is the, this is known as substrate. Substrate is the thing which actually on which the nucleophile attacks. Okay, so what we get, and Br will come out. Br is a leaving group. This is the product, and Br minus will be the leaving group. Okay, this is how the reaction happens. So this is bimolecular, because two molecules are simultaneously participating in the reaction. That's why it is called bimolecular. Okay, it occurs in single step only. But how is it possible that it occurs in single step? Actually, if you take a picture of this molecule in the middle of the reaction, okay, how it occurs? CH3 is there. Br actually is breaking away with the electrons. Okay, these arrow actually I put to represent how the electrons are coming and getting attached. Okay, and the OH minus is trying to form the bond. So this is called transition state. Okay, the transition state of Sn2 reaction. It occurs in just one step. Okay, what is the hybridization of carbon atom? Remember, hybridization of carbon. Any idea?
No, sir.
Yeah, okay. It is actually, it is tetrahedral. Okay, it is like this. Okay, this is called tetrahedral. So we put this bond, and this bond is actually away from the paper, and this bond is coming out. I will explain it in today's class, okay, regular class. So don't worry about it. So actually, when the nucleophile is coming and trying to join itself, this carbon atom is lot of crowding is there. Okay, there are 5 groups. So if you compare the speed of Sn2, or I call it as a rate of Sn2, it is going to be the fastest on CH3. As you have more and more carbon atom, this is primary carbon, this is secondary carbon, and this one is tertiary. Okay, Absad, is it clear?
Yes, sir.
So because here you have more number of carbon atom, that's why the reaction is slower. This is tertiary. Because in Sn2, 2 means 2 molecules, bimolecular means 2 molecules are simultaneously colliding and reacting with each other. So if the carbon is having a lot of carbon, means it is tertiary carbon. It is having a lot of branching. It is very difficult for the nucleophile to come and join. Okay, it will be like this. If I try to draw it in detail, it is like this. Yeah, Ryan, good evening. Can you hear my voice?
Good evening, sir.
Yeah, I was just going through the last class revision. Okay, so Sn2 can't happen on tertiary. Is it clear to everyone? Yeah, Anushka, Imad.
Good evening, sir.
Yeah. Yeah. So we were doing the same thing. Actually, I was Absar joined a bit earlier, so I was discussing what we discussed in the last class. So yeah, so we were Sn2 and Sn1. So Sn2 reaction, we were doing the mechanism of Sn2 reactions, and we discussed that how Sn2 take place. So this is Sn2 take place by the attack of nucleophile. Okay. Substitution nucleophilic bimolecular, and it is simultaneously happening. Okay, in one step it happens. Okay, Absar, that in one step
Yes, sir.
the nucleophile comes and the leaving group goes out. And look here, so bond is forming and breaking to get the product. Such reactions are also known as elementary reaction, which take place in one step. Okay? So because the two molecules are colliding with each other, the rate of reaction dependent upon the concentration of CH3Br, this one, okay, as well as this one. The concentration of both of them is important. If you increase the concentration of CH3Br, the rate is going to increase. If you increase the concentration of OH minus, the rate is going to increase. And if you increase the concentration of both of them, the rate is going to increase. It is because if you take more molecules in the same container, means more concentration, more collisions are going to happen. Is it clear? Right? Okay. So rate is directly proportional. So this is called second order reaction. Anushka, what do you mean by second order reaction? Tell me. Why Sn2 second order?
Sir, could you just repeat that once again?
Now, why Sn2 reaction is second order reaction? Why Sn2, the speed of reaction is called second order? Because there are two constants. This is constant. The speed of the reaction, this square bracket is the concentration. Okay, mole per liter. So Imad, the rate of Sn2 depends upon the concentration of the CH3Br into concentration of OH minus. Is it clear?
Yes, sir.
Okay. So Sn2 reaction, where it can happen and how it is controlled by the structure of the substrate. Okay. Substrate is the molecule on which the nucleophile is attacking. How the Sn2 is controlled by the structure of R. As you have more and more bulkier group, more branch carbon, the Sn2 is not going to happen. Is that clear? No Sn2 on tertiary alkyl halide. Imad, Absar, Ryan, is it clear? No Sn2 on tertiary carbon. Why? Because tertiary carbon, you can see how branched it is, how bulky it is, how large it is. So the nucleophile can't come in and join, can't come in and attack on the Cl, okay, CCl bond. Okay. So how the reaction happens on a tertiary substrate, that is by other mechanism, that is called Sn1 mechanism. Okay, so we will discuss Sn1, how it happens. So what do you mean by Sn1, Anushka? Tell me.
Sir, monomolecule of nucleophilic substitution.
Yeah, exactly. Substitution, nucleophilic, unimolecule. Okay, in Sn2 actually the two molecules were getting involved in Sn1. Actually, the reaction is between two molecules, but it is one by one. Both the molecules don't react simultaneously as they were doing in Sn2 reaction. Okay. Suppose if we take a tertiary alkyl halide, And here we have seen that we expected that the reaction should not happen. Sn2 will not happen. Why Sn2 will not happen? Ryan, tell me. Absar, Imad. So Sn2 is simultaneous. That's what we discussed in the last class. Sn2 is simultaneous attack of nucleophile, which is water, and the Br minus comes out. Okay. It cannot happen in this case. Why it can't happen? Rayan, Absar, Imad, Anushka, tell me why it can't happen here. Yeah.
No idea.
What's the reason? The reason is, what's the reason that the Sn2 can't happen on tertiary substrate? Very simple reason. Actually, you guys know. And the reason is because of the bulky character, bulky nature of the carbon. Is it clear? You can see the carbon is very, very bulky. Why it is bulky? Yeah. Why it is bulky? Because it is having the carbon which is attached to leaving group. Can you expect the water molecule, Anushka, to come in and attack on the carbon? Is it possible?
Yes, sir.
No, it is not possible. Why it is not possible? I have shown you here, Absar. Why it is not possible? Tell me what you can see here. This diagram. Yeah. No Sn2 on 3 degree carbon. 3 degree carbon means what? The carbon which is connected to 3 carbon atom. This one. Look here. This carbon is there, which is connected to Cl, that cannot be attacked directly by water. It is 3 degree carbon because it is having 3 methyl group. The methyl group will not let the nucleophile or the OH minus or the water molecule to come and attack, combine with the carbon of CCl bond. Okay, clear. So direct attack is not possible. But that doesn't mean that the reaction is not possible. Reaction happens, but then how it happens? If the water molecule can't attack, due to high branching on carbon. Okay. So if the water molecule can't come and attack on the carbon, directly it cannot attack, means Sn2 cannot happen. Then how the reaction take place? The reaction take place by some other mechanism. That is called Sn1. Okay. So direct attack is not possible. Sn2 is not possible. Sn1 is possible. So in Sn1, what happens? Can any one of you tell me if you have studied in school? Rayan? Yeah. Absar? Any idea? Imad? What is SN1? How it happens? Anushka, how this reaction has happened? It is by SN1 mechanism, but what actually it is? In a common man language, what it is? Yeah. So in that reaction in SN1, actually the water can't come in and push away Br because the carbon is actually covered by the methyl groups. So what happens is the Br actually slowly breaks apart. The water doesn't come. Okay. Water doesn't come because it can't come. Upsar, am I audible?
Yes, sir.
Yeah. So water can't come directly and combine itself to the carbon atom. So I have, because it is very bulky, this will not happen. So, but then how the reaction has happened? Imad, actually the Br is electronegative. Okay. And because the Br is electronegative, it has a tendency to pull because it is non-metal. And it has tendency to pull electron towards itself. Right, Imad?
Yes, sir.
So it undergoes slow ionization. Okay. It slowly break apart, right?
Yes.
And if it breaks apart, the Br will take away the electron pair because Br is electronegative, it is non-metal, and non-metals have tendency to pull electrons. Anushka, and there is a carbocation left. Is it clear?
Sir, but how SN1 becomes bulkier in this reaction? Does it become bulkier or is it already bulkier?
No, if you take a bulky substrate,
Okay.
if you take a heavily branched substrate, the reaction, the mechanism of substitution will not be Sn2. It will be Sn1.
Okay.
Because Sn2, in Sn2, the nucleophile is directly coming and approaching the molecule and pushing out the leaving group Br or Cl. But that in this case, the carbon cannot be approached because it is already having 3 carbon atom connected to it. Okay. So then how the reaction happens? That's the question. So the nucleophile can't come in and attack, access the substrate. The substrate on its own, by gaining some energy from heat or from the solvent, it start breaking and it gives us a carbocation and this Br comes out. Okay. So SN1, in SN1 mechanism, it doesn't happen directly. Ryan, am I audible? Are you getting what I'm saying? So
Yes.
SN1 doesn't happen directly. Okay. So how it happens, what the first most crucial step of SN1 is? It occurs via formation of carbocation. Anushka, is it clear? So
Yes,
in SN1 can happen only at those places where which molecule can on their own break apart from the leaving group, okay, halogen. And that happens because the cation, they can form a stable cation. So it is happening in both ways. The nucleophile can't attack me direct Upsar SN2 can't happen. But if SN2 can't happen, the conditions have become favorable for SN1. How the conditions have become favorable for SN1? Because in SN1, what happens is the nucleophile can't come directly, but the leaving group first it start coming out on its own, and this lead to the formation of a carbocation C plus. Okay, so SN1 occur to the formation of a carbocation, and this carbocation forms when the leaving group breaks apart, okay, on its own, right? So the other thing is speed of SN1, how easily the SN1 can happen, or it can happen with difficulty. Speed,
Sir, it's slow, right?
is it slow or fast?
Slow.
It is, yeah, it can be slow, but it sometimes it can be very fast. Okay, it appears that okay, slow auto ionization, but sometimes what happen is it can become faster than SN2. Okay, what you thought was correct, we expected it to be very slow, right? But sometimes it becomes very fast. So what are the factors which make it fast? So it is directly proportional to stability of carbocation. So speed of SN1 is directly proportional to the stability of carbocation, means if the C plus can form very easily, if it is very stable, then it will break apart very easily, very quickly. It appears to be a difficult step, okay, and what you thought is correct, but some factors can make it faster even than SN2 reaction. And what are those factors? The main factor is stability of the carbocation. Okay, so if the carbocation formed is very stable, then the SN1 reaction can happen very easily. Okay, so let's get into the point or the factors which make a carbocation stable. So can any one of you tell me how a carbocation can become stable? Why I am worried about the stability of carbocation? Because in SN1 nucleophile can't come in and attack directly. The leaving group break apart on its own, and that lead to the formation of a carbocation. And if a carbocation is stable, it can form very easily, right? And because if it can form very easily, then the reaction is going to happen very quickly. Okay. So in this case, the carbocation which will form is CH3 plus. In this case, the carbocation which is going to form is CH3 ethyl carbocation. And this is isopropyl cation. And this is tertiary butyl cation. So carbocation, the characteristic is carbon is plus charge, means it doesn't have any electron, complete electron. Only 6 electrons are there. It doesn't have complete bond. And the bonds are incomplete, that we know, because one of the bonded electron were taken away, snatched by Br minus, and that Br minus got apart with a pair of electron. So carbocation actually is not the electron rich species. In fact, it is electron deficient species. Okay. So this is the carbocation which is formed by this. This is, yeah. So how the carbocation becomes stable? So stability of carbocation is directly proportional to branching. If there are more and more alkyl group connected to C plus, then those alkyl group can push their bonded electrons towards the C plus, so that the C plus can get some electron and it will become stable. So tertiary carbocation is the most stable one. secondary carbocation, then primary. Primary carbocation means Apsar, it is connected to one carbon, and this is 0 degree carbocation. Is it clear? Imad, Anushka?
Yes.
Yeah.
So,
Yeah.
usually the SN1 reaction is a slow reaction, right?
SN1, we expected it to be slow, but the reality is it can be very fast also. What you thought is correct. It is actually, it appears to be slow, but it is not slow. Sometimes it can be fast. So what makes it slow? What makes it fast? You need to understand the real thing. You need to understand how this is actually, this step is the most crucial step. This is the heart of SN1. This is RDS, rate determining step, the step which controls the overall rate, which can make it faster or slower. Okay, it is actually the breaking of leaving group. It appears to be slow, but if the carbocation is forming is very stable, then the leaving group can come out very easily. It can break apart very easily. And the SN1 reaction can also happen very quickly with fast rate. So we need to discuss the stability of the carbocation. So as you have more and more branch carbocation, the stability is going to increase. Okay. Then what happens with this carbocation? How the SN1 has happened? This carbocation is now attacked by water molecule. Okay. Is it clear? You see here, this direct attack was not happening because the carbocation was very bulky, and that was not allowing the SN2 to happen. Okay. But now the leaving group has already departed with the electron pair, leaving behind a carbocation. And now the carbocation has only 3 groups, and the carbocation actually needs electron. So it can now pull the lone pair of the water molecule. The water molecule will join itself, right? Right, Anushka, are you getting?
Yes, sir.
And now, so this is going to be a fast step. This is going to happen very quickly. Apsar,
Yes, sir.
is it clear what I
Yes,
am
sir.
trying to say? So now the OH, H plus will come out, and this, all these steps are very fast. So SN2 was happening in single step where the nucleophile was coming in directly and pushing away the leaving group. Okay. And but SN1 reaction, because the carbon was very branched, so if the carbon was very branched, the nucleophile was not able to come and join itself to the carbon atom. Okay. So initially we thought that the reaction will not happen. That's what we thought. Okay, but the reaction has happened. But how it has happened? So first of all, direct attack was not possible. The leaving group actually slowly broken, leaving behind a carbocation. And if the carbocation is very stable, the leaving group will come out very easily. Okay, so the heart of the SN1 reaction is that you need to compare the stability of the carbocation in order to compare the rate of SN1 reaction. And this is called SN1, which means substitution nucleophilic unimolecular. Okay, though in the overall reaction, there are 2 molecules. In the overall reaction, you can see there are 2 molecules. But then why I'm calling it as unimolecular? It is because in the main crucial step, in the most crucial step, there is only 1 molecule. Okay, and that molecule is the substrate molecule. This is the most crucial step, in which only the substrate molecule alone is actually breaking apart. This is slow step. Okay, so but that doesn't mean that it is slow always. Okay, it can be sometimes very fast. Okay, I'm telling it relative term. In SN1 reaction, there are 2 steps or 3 steps, and within those 2-3 steps, the breaking of leaving group is the slowest. But overall SN1 can be faster also. That depend upon the stability of carbocation. Is it clear? Okay.
Yes, sir. Clear.
Yeah.
Yes, sir.
So
Clear.
yeah. So let me compare some rate of SN2. So can you tell me any other substrates where carbocation are very stable? If the carbocation is adjacent to a double bond or a benzene ring, okay, then also it is very stable. Because in that condition, the carbocation can get electron from the benzene, which is called resonance. Okay. And it can become very stable and it can react very quickly. Right? Compare the rates of SN2 reaction. For isomers of butyl bromide, bromobutane. Okay. So if any one of you need some extra session for your school exam, you can contact the management and get some extra class schedule. Okay.
Yes, sir.
So we can have some extra class or someday if you have holiday of the school and if you are free in the morning, then also you can let the management know and we can have some extra classes schedule. Okay. Or if there's some other topic which you want to study, which is coming in your school examination.
Yes, sir.
So how fast or how quickly these four molecules can react? React in SN2 reaction. How can we compare their speed of SN2 reaction? This is not SN1, this is SN2, the one which we discussed earlier. Yeah, Imad?
Sir, can you check the bulkiness of these groups?
Yeah, bulkiness you need to check on the carbon atom on which the attack of nucleophile is happening or on the carbon atom where the leaving group is attached. Yeah. Yeah, you need to think in this way only. Yeah. So what is the rate of SN2 reaction? Absar, any idea? So if you have more and more branching on the carbon atom where the nucleophile is attacking, the reaction is going to become slow and slow because SN2 means two molecules need to collide. So the carbon atom on which the Br or the Cl is attached need to be free from any crowding. Okay.
Sir, the order will be B, B, C, A, right?
Which one will be the fastest?
D,
D.
then B, then C, then A.
Is it for the SN1 or SN2 you are telling? Which one?
SN2.
SN2. SN2, it happens only in one step. Direct attack and departure. Okay. Right.
Yes, sir.
So let me show you if I am having some just a second. If we have some animation of SN2, let me show you and that will make you very clear. So it happens in one step. So you need to look at what, right? You need to look at the branching. Okay, SN2 happens only in one step, so that the carbon atom on which the attack is happening should be free from any branching. Okay, is it clear or not? Okay,
Yes, okay.
yeah, let me show you SN1 and SN2 reaction. Just a second. Just a second. OH is coming. This is the transition state, and simultaneously the Cl is coming. Right? Is it clear? It's happening in just one step. Okay. Push it out. Start with clear.
Liquid text. Winner of Apple's Editor's Choice.
And what
Most
about
innovative
the
iPad.
SN1 mechanism? So the carbon atom on which the attack is happening should be free from any branching. It should have less and less branching. Then only it can happen, come quickly. The nucleophile can come quickly and make the leaving group move out. Yeah, Anushka. So what's your answer? Tell me.
Sir, I was saying D, D, C, A.
The D is going to be the fastest.
Sir, slowest.
C or D? What you are telling?
D, D. Sir, D. A, D,
Now
slowest.
D is going to be the slowest. Okay. A is going to be the fastest. Absar, Rayan, Imad, what's your answer?
Same, sir. Actually, A was my answer.
Yeah. The D is going to be the so this is primary carbon. Okay. This is also primary, means it is connected only to one carbon. Okay. And the C is secondary carbon, means this carbon is connected to two carbon atom, 1 and 2, and D is connected to 3 carbon atom. So look at so if you have more and more carbon, Anushka, means more and more carbon means more and more branching, and carbon is a big atom, so they will cause more and more crowding. Okay, they will cause more and more crowding, and because of that crowding, what happens is the nucleophile can't come in. Okay, this we look at this picture, this one. A nucleophile will not be able to come in and join itself. But if you have more and more hydrogen, the picture is like this. Okay, if you have more and more carbon atom, the picture is like this. So SN2 will not happen on SN2 carbon. So it is going to be the slowest for D. Is it clear? Anushka?
Yes,
Rayan?
sir, clear.
Okay. So now compare the rate of SN1 for these compounds. Absar?
Yes, sir.
Is it clear?
Yeah, sir.
And what about SN1? How can you decide the rate of SN1 reaction? So look, one more thing which I wanted to tell you. These both are actually 1 degree carbon primary. Then why A is faster and B is slower than, if both are primary? Tell me.
Sir, it's because of the branching, the number of branches.
Yeah, the branching is, though both are primary, the branching is not directly at the carbon atom which is connected to Br, but it is actually, in this case, it is closer. And because this methyl group is coming out, and it will block the path of the nucleophile. So the rate will become bit less. And here the branching is directly on the carbon atom where the nucleophile is attacking. And in tertiary also the branching is maximum. There are 3 groups. So that is going to be the least reactive. Okay. So how can we compare the rates of SN1? Yeah, sir. Rayan, how can we compare the rates of SN1 reaction? So where they can, so SN1, remember how it happened. The nucleophile attack actually was not happening and starting the reaction, but instead the Br will automatically slowly will break apart, leaving behind a C plus and Br minus. So that was the most crucial step. That is known as slow step. Okay, out of all the steps, that doesn't mean that SN1 is always slower. It can be very fast, but if the slow step become faster, the whole SN1 speed is going to increase. But if the slow step is becoming more difficult to take place, then the SN1 will be very, very difficult to take place. Okay. So actually what makes that slow step occur quickly or occur more slowly? So let's check what is there in that slow step. That slow step is having what, that carbocation. Okay, so you need to look at the carbocation. So carbocation stability. Carbon is having plus charge, and carbocation is more and more stable if it is connected to more and more carbon atom, because the carbon atom help to give the electron. Okay, and that makes the C plus more and more stable. Okay, so now tell me what is going to be the rate of SN1 reaction? Absar, Imad, Rayan, Anushka, tell me. So which one can form a more stable carbocation? First of all, tell me.
Faster or slower?
Yeah, fastest.
Yeah, I think
Which one?
it's optional.
Yeah, option S is going to be the fastest. Okay, we are going to compare the stability. Actually, what happens is these alkyl groups are not electronegative like chlorine or bromine. So if there is a carbocation formed, this alkyl group, actually the bond between the carbon plus and this methyl, they push the electrons slightly towards the carbocation, and the carbocation actually gets the electron, and this is known as plus I effect, inductive effect. So the carbocation gets some electron. It is still plus, but some electron gets shifted towards the C plus. So its energy decreases, it become bit more stable. So tertiary carbocation have 3 alkyl groups. That's why it is more stable. Secondary carbocation is having 2 alkyl groups. So there is one hydrogen, but hydrogen doesn't push or pull any electrons. Okay. So this is stable, but not as stable as tertiary because only 2 alkyl groups are helping the carbocation. And primary carbocation is having only 1 alkyl group. That's why it is primary. So only 1 alkyl group is trying to push away its electron, push its electron bonded electron pair towards C plus. And if you have methyl group, that methyl doesn't have any alkyl group. Okay, so this is going to be least stable. Okay, so this is the general trend for the general pattern. In this question, this is tertiary. Okay, in this question, these are not the carbocation, and this is secondary, this is primary, and this is primary. But in this, actually, the help both are primary, but here the help is not far away. It is because the methyl group is actually bit closer to the place where the carbocation is forming. The carbocation is forming at this place, and this methyl is bit closer as compared to this where the methyl are one after another. So this being closer, it is going to give the electron more easily to the C plus, and that is the reason why the reaction can happen more easily. Okay, so the rate of SN1 is going to be S, R, Q, and P. Any doubts in this? Do let me know. Don't worry about that what I will think, or don't think like that. Okay, just let me know if it is not clear. Okay, whatever doubts are, all the doubts are very, very important. Okay, so this is the rate of SN1. So S being tertiary is going to form the cation very easily. That slow step which we discussed now, that is going to happen very quickly. Okay. So this is given in our NCERT also. So let me. Where is it? Yeah. Riyan and Abshar. I hope both of you can hear my voice. So
Sir.
Yeah, this is the SN2 mechanism. We are explaining the whole thing which I have tried to explain you. Okay, but it is very important. There are many other things also. So look, the relative rate, the SN2 will not happen on the tertiary. Look how the tertiary carbon is blocking the attack of nucleophile. Nucleophile can't get the space to come in and join itself. There is one SN1 reaction also, which actually occur by different way, which occur on tertiary, because tertiary can't take place through SN2. So actually the BR automatically slowly comes out, okay, leaving behind the carbocation, and then the nucleophile goes and join itself. This is how the SN2 happens. Is it clear? SN1 happens. So SN1, the main crucial step is slowest. It is slow and slow among all the steps because SN1 is multi-step reaction. So we need to say that which one is actually the slower step. Okay, and it is reversible, it involves breaking, and with this, all these things I told you. Okay, so you can just have look at these questions. Okay, just a second. Is it clear? So let me ask you some more questions. So where the SN1 is going, SN1 or SN2 is going to occur more quickly in these two? Tell me. Anushka, Imad, Rayan, Absar. Is the branching the main factor in this case, or some other factor is there? Yeah, Anushka.
Sir,
Imad. Yeah.
chlorine,
Tell me. Which one is going to occur quickly?
chlorine,
Chlorine or okay. So let me tell you one fact. Fluorine is second period element. Bromine as Cl is third period element. So its size is going to be larger. This is going to be smaller. Absar and Rayan, the Br is fourth period element, and iodine is fifth period element. And if you have larger and larger atom in the periodic table, if you look at them, okay, they are actually one below another. So if you look at their size, okay, so if you have a larger atom, it's definitely its bond electron are going to be very spreaded in a very large area. It is going to be weaker. Is it clear? And now tell me, here the
Sir,
branching,
will be iodine.
not the factor. Yeah, now tell me.
Sir, iodine.
Yeah, iodine. Iodine is can come out very easily. First of all, there are two factors that can break away very easily, being very long bond. Small bond, the electron density is more tightly holding the two atoms together. The long bond, Imad, can break very easily.
yes, sir.
Okay?
Yeah.
And I minus is very stable because the minus charge as compared to Cl minus. So both have -1. But that minus on a very big atom doesn't create any problem. But minus on a very small atom lead to increase in potential energy. So that is good leaving group also. It can come out very easily. And the bond is also weaker. Absar and Rayan, is it clear or not?
Clear, sir.
Yes, sir.
So what is the rate of Sn2 in this case? Sn2. This one. Yeah, Ahmad.
CH2Cl.
Yeah, why it is CH2Cl?
So because I think it's a primary highlight.
Yeah, primary it is actually coming out of the chain. But here the Cl is directly connected to the cyclic ring and it has two carbon atom. So it is branched, more branched, and this is actually a branch coming out, and that is the ring is left behind. Okay. Is it clear? So that you need to understand. Yeah. So for isomeric bromobutane, the question which we did just now, what is the rate of Sn2 reaction? I hope you can do. Okay. And what is the rate of Sn1 reaction? That also we did. So we can do it on this one. This question is very, very important. So first tell me what is the rate of Sn2? I will give them a sign P, Q, R, S. Okay, you need to tell me the fastest first. I think so. Just a second.
Sir, for this question, I think S is the fastest. P is the slow.
S is the fastest. Why it is the fastest?
Because 2 secondary bromides.
Yeah, it is like this. Be very careful when it is written that the Br is connected to this carbon.
Okay.
So carbon, this is one benzene ring. Okay. So everybody listen very carefully. Rayan, Absar, there are this C6H5 is the phenyl ring, which is benzene. There are two benzene ring and there is one methyl group connected. Carbon is tetravalent, means it need to have 4 bonds. So another is Br. So this is the detailed structure, Anushka, of this molecule. Now you can write the detailed structure of all of them. So the carbon is having H, methyl, PH, Br. The detailed structure of R. And this one. Now you can compare. I will write their structures. In the meantime, you can think. This one is benzylic bromide. I will write it in short. Instead of drawing the complete benzene ring, I will write pH. pH C H H Br. And guys, remember the pH is a very big molecule, very, very big. Okay. And this is pH C pH H Br, right? And this is going to be the, I will write it here, pH C H CH3, right? Br. Okay. Yeah. So now tell me what's going to be the rate of SN2 reaction. Yeah, Imad, Absar, that the hint is, okay, the hint is that you need to think where the steric hindrance is more or less. That you need to think. Okay. Now, what's going to be the answer? For SN2 reaction and SN1 reaction also you can try. Yeah, Anushka. Which is the most bulkiest? Which carbon having the maximum crowding? And that is going to be the slowest for SN2 reaction. Yeah, Imad.
So
Which
P,
is the most bulkiest? P, which
P.
is having P, Q, R, and S, which is the most bulkiest, the slowest one.
So
Which will be the slowest?
for SN1, SN2,
SN2.
SN2 slowest. Lowest SN2 P, I think.
Which one?
P, option P. Please.
P, first one.
Yes, sir.
Why it will be slowest?
I think so because uh, double carbon bond and then
Is it the most bulkiest one? Look here. Is it the most bulkiest one?
I thought so.
No, this is the most bulkiest. Look here. Why it is the most bulkiest? Why? Look at the structure. There are two benzene rings, one methyl, two benzene and one H. Just one benzene. So if you have just one benzene ring and more, as you are having more and more hydrogen, the crowding is less and less. Because hydrogen is the smallest atom. So Sn2 rate is inversely proportional to crowding. If you have more hydrogens, means more easily the Sn2 can happen. Anushka, is it clear or not?
Yes, sir, clear.
So where it is going to happen more quickly, you need to compare the hydrogen not everywhere, only on the carbon atom where the Br is connected. So P is the fastest. Okay, and now here you doesn't have any hydrogen on this carbon atom. Okay, where the Br is connected, this is going to be the slowest. So the slowest one is going to be S. Okay, and between Q and R, you have two phenyl group and you have methyl group. So Q is more bulky and R is going to be more quicker. Is it clear to everyone? Look here. Okay, so this is slower. Why? Because two phenyl rings are there, and one phenyl, one methyl, one H, only one phenyl and two H. Apsar, are you getting what I'm trying to say?
Yes, sir.
Okay, Anushka, Rayan,
Yes, sir, understood.
yeah. And what about SN1? SN1 actually you don't bother about the branching, IMAD and all, because there the nucleophile can't come in and attacking directly. But in SN1 you have some other worries, other things to worry about. What are those things? Yeah. Yeah, Apsar. SN1 rate means speed is directly proportional to C plus. Okay. If the cation, because that was the most difficult step. Okay. And if the cation can form easily, the SN1 can happen easily. Okay. And let me tell you one very important characteristic of benzene. If you have a benzene ring, the benzene helps the carbocation because benzene has a lot of electrons in it. It gives its electron, loose electron because there are double bond. It gives its electron to carbocation. Okay, and that's how the reaction can happen more easily, and more benzene means this cation is becoming more and more stable. So more branching, more bigger groups means Sn2 will not happen. Sn2 will become less and less. But if you have more bigger groups, more branching means what? Means more Sn1, right? Okay. So tell me quickly. So what will be the rate of Sn1 for these? Yeah, I have written their structure. This is in detail I have written. Yeah, Apsar, can you hear me? Rayan, Apsar and Rayan, both of
Yes,
you.
sir.
Yeah, so the Sn1, Sn2 are actually opposite to one another. If you have more branching, means more Sn1, more but less Sn2. Okay. Sn2 because more branching will prevent the attack of nucleophile. Yeah, so where the reaction is going to be quickest. This molecule is P. Let me change the color. This is P, Anushka. This is Q. Rayan. This is R. No, this is This is not R, this is S, and this is R. Now compare and tell me where the reaction is going to be the fastest. SN1 I am asking. Yeah guys, come on, tell me quickly. Where the SN1 is going to be the fastest. Tell me the fastest first. Yeah, Anushka?
Sir, it will be S.
Yeah, S, fastest SN1. Why?
Sir, because it's more stable.
Because it's,
More stable.
yeah, actually when the BR, you need to say that when the BR comes out and when there is a carbocation formed on this is the carbocation, that will become very stable because it is having two benzene ring and they have loose electron, lot of 6 electrons, 5 electrons are there, they can give that electron to that carbocation. There is one methyl group also that can push away its electron to carbocation. Okay, right? So carbocation can become more stable, and if it can become more stable, then it can form very quickly. Imad, is it clear?
Yes, sir.
So here also it is stable, but not as stable as the one in which, so this is the fastest. So let's compare the rate. S is going to be the, so more benzene rings will make carbocation more stable. So S, then you have Q. There are 2 benzene rings, okay, right? And then you have R. There is one benzene and one methyl, and the SN1 rate slowest is going to be your P. Is it clear to all of you how we decide the rate of SN1 and SN2? Okay.
Yes.
So look here, guys, how the double bond stabilize the cation. Look here. So if a cation is formed and if there is a benzene ring, the benzene ring is actually a blessing for the cation. Okay, it can give its electrons outside. Okay, and the cation is going to come here. This cation can get the electron from the double bond which is next to it in the ring. So it can come here, it can come further here, it can go back to its original place. So it will keep on moving, it spreads actually at many places. Okay, and if the alkyl group is same, you need to compare the bond strength. If the alkyl group is same, you need to compare the bond strength. Iodides are weakest, they are going to react more quickly. Follow the bromide, chloride, and fluorides. Okay, so I hope this is clear to all of you. Okay, now we need to compare their stereochemical aspect and all. Okay, actually, suppose sometimes when we are going with an umbrella, okay, and if there are strong winds blowing, what happens to the umbrella? It gets flipped. Okay, the umbrella become like this if the strong winds are blowing. At some point of time you might have experienced or you might have seen it. Okay, so in SN2 also there is a nucleophile coming, there is a leaving group going out from this side. So what happened to the 3 bonds? What happened to the 3 bonds? They get flipped away. They actually move like, okay. So stereochemistry of SN2.
Sir,
Yeah.
sir, I'm currently using my phone, so I'm facing some problems. I have to switch to my laptop, so I'll have to leave for a minute.
Yeah, yeah, you can rejoin, no problem.
Thank you, sir.
So stereochemical aspect of Sn2 and Sn1 means what happened to the structure of that the leaving group get attached. If you try to look at the bonds, okay. Now you need to understand the details, right? So Sn2 in Sn2, I will say so nucleophile has to come and join from the side opposite to the leaving group. Why it is necessary? Why it is compulsory? Because suppose if Br is there, the nucleophile is also coming and joining itself to this at the same point of time. Okay, so if the Br is leaving, nucleophile is coming. Ryan, Absar, the nucleophile has come from the side which is opposite to the leaving group, Imad, right? So what happened to these three bonds? They're like this, nucleophile is coming, okay? And when the nucleophile get attached, they become like this. They go other side, okay? And this is known as, so if you have nucleophile attached, it becomes like this, okay? And this is known as what? This is known as inversion of configuration, right? Inversion of configuration, okay? So why there is an inversion of configuration? Tell me quickly. Rayan, can you hear me?
Yeah, sir.
Yeah, yeah. Why there is an inversion of configuration happens in Sn2 reaction? How we will explain it? Yeah, the reason is that the nucleophile has to come from the side opposite to the leaving group. It is because it is happening in just one step. So in one step, you need to break the Br, you need to bring in the nucleophile upsar. So it is very important that the nucleophile should come from this back side. Okay. And if the nucleophile comes from the back side, so what happened to the three bonds which are neither nucleophile nor leaving group, they turn opposite side like this. So inversion of configuration occur, okay? Inversion of configuration takes place, right? So this is how it happened. This is how it happens, inversion of configuration, and this is known as Walden inversion. Okay, it is mainly experienced when you have four different groups. If you have four different groups, that is known as chiral carbon. Okay, chiral carbon is a carbon which is having four different groups. Okay, So there you experience it more easily, that wherever the nucleophile comes and join the bond, change their side. Okay, so suppose if I ask you in SN2 reaction, suppose this is H and let's say this is CH3. What does this bond mean? This is known as wedge and dash representation. So one is wedge and this is dash. So here you can see all four groups are different. What do you mean by wedge and dash, Imad? Is what do these bonds represent?
Sir,
Configuration.
Yeah,
sir, the
this
dash means that the group is leaving and the wedge means that the group is attaching.
the wedge indicates that the group is coming out of the plane. It is coming towards us, up. It is coming up from the paper, and the dash means it is going behind the paper, below the paper. And normal lines means these groups are in the paper. Because carbon is not planar, the four bonds are not in the same plane. Okay, this is the three-dimensional representation. Okay, so this is the nucleophile, and the nucleophile, because it is this is SN2. In SN2, actually, the nucleophile has to come side up from the side opposite to the leaving group, so it has to come from the back side. Okay, and the leaving group comes out. So what happened to these three bonds which are actually participating? They're like this. Okay, so this for this I will use dash because it is behind the plane. For this I am going to use wedge. Okay, this is directly in front of the camera, you can see it. Okay, this one, this I am going to use dash. Okay, so the nucleophile actually comes and push away the Br. So what happened to these bonds? They move like this. Okay, the all three bonds, look here, they were on the left hand side. I have flipped them like this, like umbrella. Okay, this is known as inversion of configuration. Okay, is it clear?
Yes, sir, clear.
And this molecule is known as chiral. Chiral molecule. Chiral molecules are actually optically active. They rotate the polarized light. Okay, so it is connected to four different groups. There you observe that the inversion occurs. So in SN1, what happens? So the molecule which you are going to form in SN2 will be just the opposite. the 3 bonds which were on the one side, you need to flip them to other side. Okay, and that this is known as inversion. While in SN1, so now my question is, in SN1, where the bonds will turn up finally. In SN2, they moved on the opposite side. But in SN1, actually, 2 molecules form. So this is a branch substrate. Okay, Upsar. And here the nucleophile can't come in and directly attack because it is a very bulky, right? pH is C6H5, methyl is there. Okay. So what you do in SN1, the Br actually first breaks slowly away from the molecule and you have this cation. So now my question is, just like in SN2, we flip the other 3 bonds on the other side. What will happen if the carbocation is forming? What will happen to these 3 bonds? Okay, these 3 bonds are flat. They become flat or trigonal planar. They are like this. They are not on any other side. Actually, in SN2, it happened that they were one side, and when the nucleophile was coming, they moved other side. Okay. But suppose if the leaving group comes out before the attack of nucleophile, that is SN1, unimolecular. Okay. So what happens to the carbon? How it look like? Are the 3 bonds on one side or the 3 bonds on other side? The answer is the 3 bonds which are there on the carbocation, they are flat. Carbocation is a flat trigonal planar species. Okay. And it has a plus charge. Plus charge is actually because of the empty orbital, p orbital, which doesn't have any electrons. So I'm making a p orbital perpendicular to the 3 bonds. Okay, and this is the p orbital, and this is empty. Okay, this doesn't have any electron. That's why there is a carbocation, and these are this is the position of the bonds. Other bond, they become planar. Okay. Now the question is, from which side the nucleophile is going to come in and join itself to the carbon atom. In SN2, there was a compulsion that the nucleophile has to come only from the side opposite to the leaving group. Otherwise, the nucleophile can't come in. Okay, because all the things are happening in a single step only. So they need to be very systematic. From this side, you need to enter. From that side, you need to go out. Okay. But in this case, the leaving group has already departed, leaving behind a flat carbocation. So the carbocation is sp2 hybridized. Okay, if you want to get into detail, that is flat. Now my question is, from which side the nucleophile is going to come and join itself? The answer is, because the carbocation is flat, it can be attacked by the nucleophile from any of the sides. Because it is flat, there is nothing to guide the nucleophile, nothing to make the nucleophile come and join in from that side or this side. Okay, that there is nothing like that. Okay, nucleophile can come in from any of the sides, right? So if the nucleophile can come in from one side, you will get one isomer, and if the nucleophile comes in from the other side, you get another isomer. So you get this kind of structure. This is nucleophile. Okay, this is pH, this CH3, and this is H. Okay, and that's the other structure is, I also have the models. I will show you. You need to wait for 1 second. Just I will bring them my models. Okay. So you get two mirror image isomers, right? So just I will show you just so these two molecules are known as racemic mixture. These are two mirror image isomers. Okay, so these are the models, right? So you can see. So are they same or different? Rayan, are they same or different? Imad,
Sir, they are different.
they are same, Imad.
Yes.
Okay, and Anushka, what's your answer?
Sir, they are different.
They are different. Rayan and Absar, they are same or different?
Sir, different, sir.
Different. Yeah. Actually, they appear to be same, but you need to check them very closely. Actually, if we try to superimpose them, they are mirror image isomers. Okay, you can have a look that if you try to touch them to the mirror, Rayan, they are mirror images of one another. Okay. So they are not same, they are different, because if you try to superimpose them, look, am I able to overlap them on one another completely? Look, these blue and the red and yellow are not matching. Is it clear? And the yellow and the red and blue are not matching. Is it clear, Imad?
Yes, sir. Okay.
Okay, so they are different. So this is a chiral molecule. Chiral molecule, it is the chiral carbon. Okay, the carbon which is connected to 4 different groups. Here the groups are nucleophile, pH, methyl, and H. Okay, and this is how the carbon look like. And if the carbon has 2 groups connected, 4 groups, all 4 groups different connected, it is known as chiral molecule. And when you pass polarized light through it, the light rotates. So it is optically active also. And this is another form of the same molecule, okay, which is actually the mirror image of the same molecule. Okay, and that also is chiral, because the carbon is connected to 4 different groups, but in different order. Okay, because if you come move from red, yellow, blue, one is anti-clockwise, another is clockwise, red, yellow, blue. Okay, so both are chiral molecule, both are non-superimposable mirror image isomers. Okay, so in SN1 reaction, both form. Okay, both form in equal amount because you have a flat carbocation and the nucleophile can come in and join from both the sides with equal probability, and due to which you get the both the molecule, and this the mixture is known as racemic mixture. Okay, now the mixture of two molecules is not optically active. So in SN2 reaction, the inversion occurs, only one isomer is formed in which the nucleophile is connected from the side opposite to the leaving group. But in SN1 mechanism, you have both the isomers formed because there the nucleophile has can come and leaving group has already departed. So there is nothing which can guide the nucleophile. Okay, to come and join from only one side. It will come and join from both the sides. So you will have these two isomers, and I have shown you the models of these two isomers, and with that you can understand. Okay, this is the plane polarized light optical activity. Okay, this you can see. Okay, I will show you what is plane polarized light and parallel molecule. Okay, so in SN1 you have, look, these are the models which are shown. Okay, racemic mixture being formed. Is it clear? Is it clear to everyone? Racemic mixture
sir.
forms, and in SN2, yeah, SN2 inversion occurs. Okay, so this is the detail. You can read it. I have explained it to you. Okay. Retention and inversion both happen in inversion. They have explained what is inversion and retention. One is retention means on the same side, and one in inversion actually. So in SN1 both happen together. Okay, 50-50 mixture of the two, and that will not rotate the plane polarized light. Okay, so polarized light, yeah,
Sir, could you just say the meaning of racemic mixture again?
racemic mixture, yeah, racemic mixture is equimolar mixture of two enantiomers. Okay,
Yes, sir.
equimolar mixture of two mirror non-superimposable mirror image isomers is known as racemic mixture. Okay. In SN1, racemization occurs. Okay. In SN1, the racemization occurs.
Yes, sir.
Racemic mixture is formed, and the overall product, because it is having the two mix molecules together which are mirror images of one another. Okay, let me show you what is polarized light. Light actually is oscillating electric and magnetic field, and this is a mixture of light which is it is a wave nature, and it is actually oscillating in all the directions. Okay, that is non-polarized light, and once you pass it to polarizer, the plane is, so depending upon the crystals of the polarizer, you can see it will actually make it will let only one light to pass through it, and the other lights are blocked. Okay, so that is called plane of polarized light, and when this light is passed through molecule, when this light is passed through optically active molecule or chiral molecule like this, because it has 4 different sides, the plane of polarization rotate clockwise or anti-clockwise. Okay. And there is the substance which rotate the plane. This is the plane of the polarization, the final plane in which the light is moving, the wave of the light is moving. Okay, that is called plane polarized light, right? But this is the plane of polarization. And when you pass it through organic molecule, if it is having a chiral molecule like this is the model actually, not the actual molecule. It will rotate the plane of polarized light. The plane of polarized rotation can be either in clockwise direction, that is called dextro-rotatory or levo-rotatory. So in Sn2 reaction, you get only one of them. You don't get both because there is an inversion take place. So, and you have to attach the leaving nucleophile from the side opposite to the leaving. Okay, but in Sn1 mechanism, both forms. Okay, so both the mirror image form. So one molecule is dextro-rotatory, another is levo-rotatory. Okay, means one molecule rotate the plane because both are mirror images. So one molecule rotate the plane of polarized light in clockwise direction, another molecule rotate the plane of polarized light in anti-clockwise direction. Okay, by the same magnitude. And if you mix them together, there will be no rotation because both molecules are formed in equal amount. They will cancel their rotation. That is called racemic mixture. Is it clear what racemic mixture is? Okay.